Okay, good morning. How's the HMM thing going? It's supposed to make you have to tear your hair off. If you haven't gotten there yet, you're not far enough advanced into testing it. It's tough. It forces you to deal with tiny little details and boundary conditions and floating point limits and the algorithm itself and understanding what's going on. But when you emerge from it, you really understand HMMs in a way that you don't understand them any other way. That's been my experience. Okay, we're entering the finish part of the course. We have a bunch of lectures left that are sort of unrelated. They could be taught in any order. They're all pretty much build on things we've done before. We're going to go back to EM probably next lecture, next Tuesday. You've heard about EM when we did the HMM learning. I just mentioned it's a special case of EM. It's hard to see, when you learn EM, it's hard to see the connection in the beginning because it is a very special case, but it's a very common special case that applies in many other cases too. Today we're going to talk about a kind of learning that's very different than what we've done until now, but not surprisingly it's been done in statistics before under different name and different guys and slightly different emphasis. So we're going to make the connection to statistics as well. I'll start by just giving you the basic idea. What we've done until now in machine learning is define hard bias, introduce some kind of a language to describe hypotheses, either a parametric language or some other kind of language, and then somehow use the data to zero in within a hypothesis space on one or more hypotheses that we were interested in, and we talked about the learnability of this class, and we talked about how do you know when you find a hypothesis whether it's what its true error rate is, and we tied it to concepts in statistics having to do with estimators and bias and variance and the maximum likelihood principle and the prior and posterior and base, and then we talked about modeling time sequence with a hidden state and the Markov assumptions and HMMs. What we'll talk about today is a very different kind of learning, which some might think is not learning at all, but it's a fair competitor alternative to learning, and that is more or less memorization. So the idea is that when you get your training examples, you just memorize them, you just store them in some convenient way, and you don't worry about it until you're asked to classify a new example. So the method I'm going to use is used for classification. It actually can be used also for regression. If you remember what regression is, it's basically trying to predict a numerical value of a function from input. Whereas classification is trying to choose one of a finite number of categories from the same input. So the method I'm going to describe is used actually for all three things that you can do with data, which is classification, regression, and density estimation. Did I mention these three to you before, the Holy Trinity? Okay, so classification, I'll just go through it really quickly again. Classification is the task of given input deciding on a discrete output from a set of finite outputs. Typically two, there will be binary classification, or it could be more. Regression is same setup, but what you're trying to produce is a number as an output. And you're usually measured or evaluated by how close your number is the correct answer, as opposed to in classification is did you get the right class or not. Density estimation is trying to estimate the probability density function, some probability density function from examples from it. So that would correspond to you're given a set of numbers and you're trying, let's say you're told they came from a Gaussian, and you have to estimate the mean and variance of the Gaussian. There's no classification involved, there's no regression involved, there's no x and y, there's just x. And there are lots of examples of x, and you're trying to understand the distribution from which they came. Okay? The method we'll discuss today can be used and is used for all three. So we'll start with classification. Tom?
What about the problem of trying to find a minimal function?
Finding a minimal function I don't usually think about as a problem in statistical estimation or in machine learning. I think about it as a problem in math.
Well, it's sort of genetic algorithms are designed to do that.
I suppose. So you can think about finding a minimum in general math theory, calculus or something else, or even algebra, or you can think about it as a search problem. If you cannot solve it through analytical methods, you can think about it as a search problem. And as a search problem, it fits into AI.
Yeah.
And within AI, you have gradient descent, and you have genetic algorithms, and you have... Yeah, but that's more, strictly speaking, it's AI as opposed to machine learning.
Okay.
That's my way of thinking. Other people might include it. Okay, so here's the general idea. Let's say we deal with binary classification. We'll talk later about how we generalize it to other classifications and to regression and to density estimation. But binary classification, you have a bunch of the data points that are labeled as plus or minus, and let's say for simplicity that they are in 2D space. So x is taken from two-dimensional space, and y is taken from plus or minus. Classic classification problem. And because I chose it to be in two-dimensional plane, I can just draw them on the board as examples. Plus, minus, minus, plus, minus, plus, minus. I don't try to make sense of them. In the past, what I did was try to assume maybe there's a perceptron, which means a straight line that separates them, and maybe there would be, maybe there won't. Or some other curve family. I'm not trying to make any sense of them when I collect them. I just store them. And then I'm given a new instance, a new input, which I'll call xq. Q for query. It's right here. And I'm asked to classify it. Is it positive or negative? Based on the examples I've seen so far. And my method is going to be very simple. I'm just going to look around, find who's my nearest neighbor. This guy is my nearest neighbor, so I'm going to classify this as positive. That's it. End of story. It's called the nearest neighbor method. Now comes the hard part. What do you think about it? Is it good? Is it bad? Is it ugly? When will it work? When will it not? What does it assume? Anything you want to tell me about it? About this method? Please.
It's not always easy to define proximity.
It's not always easy to define proximity. You mean to define distance?
Yes.
Okay. So my definition of distance here between xq and some other xi is going to be the Cartesian distance, namely the square root, or I should make it in general in n-dimensional space. It should be the sum of xqj minus xij, so the jth coordinate, squared, and then all of this is taken, this goes from 1 to n, and this would be, I'm sorry, half for square root. So this is the usual definition of Cartesian distance. I mean, you're right. I mean, I agree with you, but I'm saying let us assume that this is our distance. I don't even have to take the square root at the end, because whatever thing will minimize the distance will also minimize the square distance.
The nearest neighbor could be an outlier and it could have made the wrong decision.
I'm sorry?
If the nearest neighbor is an outlier and it's a misclassified example.
If your nearest neighbor is an outlier, it would make the wrong decision. So that would correspond to a situation where, let's say you have lots of x's around here, this looks like a clearly, pluses, a very positive area, but for some reason there's one exception here, an outlier of sorts, but it happens to be closest, and you're saying then it will make the wrong decision. True? Well, if you call that the wrong decision, yes. It will make a decision that you may not like. May not be true. True? You're saying that it's influenced, it's sensitive to fluke events, whereas a classifier that's based on averaging of some sort would be less sensitive to fluke events. This can be influenced by one event. Yes.
Is it sensitive to the order the examples have been given in?
Sensitive to what?
The order the examples have been given in?
Not the way I defined it. No. You could imagine making it sensitive to it.
I was wondering, like, after you've classified XQ, are you going to use it in the classification of the next point?
Fair enough. If you do, that's some kind of an online learning. But typically, you're assuming that once you made your prediction, you're given the correct classification, so you can change the label. But that's not the setup I was describing. You just have a fixed amount of data and then training.
Sensitive to noise?
Sensitive to noise. What do you mean by that?
Well, if the points you get have some noise, so they're not exact. So because of the noise, it's closer to positive and negative when it's actually negative.
So there are different kinds of noise. I think
Random noise. There's random noise in your data.
Right, but even different kinds of random noise. So one noise would be that the labels might sometimes be wrong. Okay, and that has more to do with your point, that maybe this outlier was just because of the label being applied incorrectly. But I think you were talking about a different kind of noise where the location of the point. So label being wrong is a noise in Y. You're talking about noise in X, where the coordinates are kind of moved a little bit, and that could move the decision. Sure? Please?
We can classify it accurately if the distance to the nearest neighbor is very far. So in very large dimensional spaces where the...
Okay, I like that. So let's see, your data is not distributed uniformly through the space. I mean, it happens to be concentrated here, but there's also data here. And all over the board, various degree of density. And if your new query point happens to be here, it looks kind of an iffy classification, because there's really nothing around it to tell you what's going on, and you're relying on something that happens far away, and is this really much closer than this? I mean, that's another thing that's related. What is the nearest point and the next nearest point? The nearest neighbor and the next nearest neighbor are really not that far apart in their distance. One is distance 5.3 and the other one is 5.3 and 1. Okay, they're very, very close, and one of them is positive and one of them is negative. It looks like you're making a somewhat arbitrary decision there. Although you could argue that if you have to choose one over the other, you might as well choose the nearest one. Please? That's a good one. It actually can take quite a bit of computation to find which is the nearest point. So, suppose you had 1 million data points, which is not unreasonable. And suppose they were not in 2-dimensional space, but they were in 50-dimensional space, which again is not unreasonable. I mean, you may think, we don't live in a 50-dimensional Cartesian space, but often this method is applied to attributes. If the attributes are numeric, then you can think about them as if you have 50 attributes, you're in a 50th dimensional space. And if it's 1 million data points, and each point has 50 dimensions. To find the distance to each one of the points, you have to do this subtraction and squaring 50 times, right? The 50 items here. So n equals 50. And then you have to do it for all 1 million of them. You got 50 million calculations for each classification. On the other hand, if you compare this to another learning algorithm, often learning algorithms have a lot of computation to do during the learning time, when they keep track of the version space, or they take the derivative and they do gradient descent, or whatever they do. If you compare it, say, to neural networks, there's a lot of computation in neural networks in training the network using the forward-backward algorithm. It can take hours and days to train it. Once it is trained, using it to classify or regress on a new input is instantly. You put it in, you propagate the values forward, and you're done. So neural networks take a lot of computation to train, to learn, to fit, and very little computation to use. The same is true for decision trees. Building decision trees is computationally hard. If you have a lot of data and a lot of attributes and you try many of them, and especially if you allow yourself backtracking and all sorts of other tricks, it can take a long time to build a decision tree. Once a decision tree is built, using it takes very little computation, even less than neural networks, because you just put your instance at the root and you propagate it down to the leaf, and you basically ask as many questions as there are along the path. In contrast, the nearest neighbor method is exactly the opposite. Learning time, you really don't do any learning. You just memorize, you just store it. When it's time to classify, you have to do all this hard work of comparison. It's busy work, it's stupid work, but you still have to do it. So there's a trade here between learning time, or training time, let's call it, and test time, or use time. Now it turns out that you could actually trade off, even within the nearest neighbor, you can do some trade-off between these two. So sometimes you're in a situation where you know that you're going to get a lot of data, and the data is going to change all the time, your training data, and then you only use it a few times to classify new instances. So you don't want to spend a lot of time here. You might as well spend your time here. Other times, you may get one batch of data and it's supposed to last you for the whole year, during which you will be queried millions of times. In which case you may want to optimize as much as you can the querying stage. Minimize how much work you need to do there, but doing some work ahead of time. Can you think about how you might do that, for example?
Please. You say some heuristics or some distances prior, so that we can then use these properties to derive distances from the data.
Okay, so you do some pre-processing to allow you to later on, once you give it a new query point, more quickly find the nearest neighbor. Right? Can you think of some things you could do? Then?
Yeah, we just split the plane into, tile the plane basically into surfaces, and pre-compute those surfaces so that if you're given a certain point and you find that it is within a certain surface, you can basically say what the nearest neighbor is.
Okay, so alright, I'll do it here. If you see this negative guy and he's surrounded by positive guys, and here's a negative one, you can, with some thinking, derive the boundary, the decision boundary between them. Like between these two, it'll be right in the middle, and then it'll come to here, and then there's these two, it'll be like this. Let's not worry about what's happening at the bottom. Here it'll continue this way. Let's work on this guy. It's still positive all the way to here, because these are all positive. And here, it might be negative from here on. Not sure. It may actually take some thinking and computing to do it, but in principle, once the points are laid out on the board, they define decision boundaries. They define cells that, like, let's say the cell for this guy is something like this, that defines all the points that for which this is the nearest neighbor. And even though here it's no longer the nearest neighbor is this one or this one, but it's still a positive. It doesn't matter, but from the point of view of this guy, anything that falls under his influence is positive. So you could think of potentially in advance parsing out the space and saying what belongs to which. It works in low dimensions, like 2 dimensions. It doesn't work so well in 100 dimensions, because the number of such cells is going to grow exponentially with the number of dimensions. You could, for example, use a triangle inequality to reduce the amount of computation you do, even without pre-processing the data. So this is a way of cutting down on your test time work. For example, suppose your new point is here, and suppose by some heuristic maybe you suspected that some of these points are nearest to it, maybe by finding out which quadrant of the space they're in, or some other coarse calculation which we can talk about later. But once you found at least one point, let's say this one, and its distance, now you know that you're only interested in points that are at least as close as this one, or closer. Now when you examine some of the other points, after looking at one dimension, you already know that they'll never be good candidates. They're too far along that dimension. So as you build the distance, as you exceed the minimum distance achieved so far, you don't have to keep calculating. Right? You can do that with no pre-processing. So that uses the triangle inequality in the sense that you're saying that this does not use triangle inequality. Let me show you something that does use triangle inequality. The qualitative idea of triangle inequality is that if a point A is near point B and point B is far away from point C, then point A is also far away from point C. Okay? So if C is our desired point xq, and I found that this point is very far from it relative to other points, then any point that's close to this one is automatically known to also be far enough not to be considered. So if you can pre-process your training data and form clusters or cliques or groups of points that are known to be close to each other, when you exclude one of them, you can exclude all of them. You have to be careful about exactly how you apply it, but within bounds of margins. So if you're close to something that's far, you're far also. Similarly, if you're far from something that's close, you're also far. Right? And if you're close to something that's close, then you're likely to be close. The only way it doesn't work is if you're far from something that's far, that doesn't mean you're close or far. You could be either close or far. But you can use the first three to pre-process relationships between your data. There are actually many other things you can do. There's been a lot of work on pre-processing data so that you can find nearest neighbors quickly. There are all sorts of tricks you can use. You can use hashings of different types and coarsening of the space, and the trees that you can build in this. For example, using the data, you can pass a long line in some direction and keep track of the projection of all the points on that line. And then pass another line. You can pass them in the directions of maximal variability. And then you can try to coarsely classify points according to how far they are on this line. And again, make reason about it. And you can imagine there could be some algorithms that would occasionally make mistakes. So heuristic algorithms that are not guaranteed to give you the nearest neighbor. But then again, the whole method is a heuristic method. The fact that something is closest to you does not guarantee that it gives you the right answer. So you may be willing to use a method that will not always give you the closest point. And there are many algorithms that are guaranteed to give you the closest point and would run very fast. But all of this is to impress upon you that when you use a method like this, you're throwing all the computational challenge on the querying time. There's another name that this goes by, and that is lazy evaluation. As opposed to eager evaluation. So actually the distinction between eager and lazy evaluation goes beyond the issue of when you do all the computation, but it's characterized often by do you eagerly, as soon as you get all your training data, do a lot of work, make some decisions, and then later when you get your test data, apply it simply, or do you lazily store the data and worry about it later? It's not just a question of laziness or of when the computation is done. It's also a question of, do you make commitments in advance? Do you make decisions in advance? Or do you remain agnostic and you say, I don't know anything about the world, I'm not going to choose a prior, I'm not going to choose a bias, I'm going to only make choices when I'm faced with having to make a decision. If you want an analogy, very hokey one, I agree. It's between someone who is dogmatic and has a clear philosophy, either a religion or some other philosophy, economic philosophy or whatever of life, and they know exactly the answer to everything. And then as life hits them, they just apply their philosophy or their dogma to get the answer. And on the other side, there's someone who lives without a philosophy but make decisions on a case-by-case basis. Kind of a philosophical analogy of sorts. Okay, so this is as far as computation. What else do you think about this method? Ben?
Well, I used it once. I didn't know that this was the same, but it depends a lot on the problem. If the problem is in some kind of spatial locality, for example, we put a sensor on a person and we saw, well, it was an accelerometer, so it would tell us how fast it was moving, basically. And we were trying to see what it was doing. So in that case, if the sensor gave us a lot of input that varied, it was clear that the person was moving or running or whatever. So in that case, I think this can be used very well, because we know that if we get points in a certain area of the space, for example, we know that well, we can identify what the person is doing. In this case of just seeing whether a point is on a surface or not, that might not be the case. I think it depends a lot on the problem.
I like this answer. It absolutely depends a lot on the problem. Some problems it would be appropriate for, and some problems it will not. Some problems it would give you very bizarre answers. Can you try to further characterize for me under what conditions you think this... What exactly is the assumption that we're making here? Whenever you do learning, you make assumptions, right? Whenever you make predictions, you make assumptions. I hope I convinced you of that. Neil?
It assumes that if two points are close together, then they have the same classification.
That's perfect. That's the answer I was looking for. It assumes that the labels of the points that are close together, tend to have the same label. That's an underlying assumption. I think this is really what you were trying to get at. In some circumstances, this is a very reasonable assumption. In other circumstances, it's not. Any problem that you see either with this assumption or with something else? Any difficulties? So then the example that you gave was there were lots of measurements. How many attributes do you remember?
It depends. What we did was very simple, but I read a paper of some people who actually had sensors to see whether the person was sweating and something about the noise around the person, so it was pretty complicated, so you can get really large amounts of it.
Okay, so let's consider some of these attributes. Let's say measure whether the person was sweating. That was measured by electrical conductance of some sort. So I don't know what units you use to measure electrical conductance, but let's measure it in sweat drops. Okay, so x1, or the first dimension would be what do you call it, dimension 1, would be measured in sweat drops. What else? What else were you measuring, or was the paper measuring?
Amounts of acceleration.
Okay, that's measured in meters per square inch, acceleration per second squared. Meters per second squared. What else? Decibels for the noise. Okay, do you guys see where I'm going? Often the attributes have different dimensions. They're not directly comparable. So how do you measure distances in a high-dimensional space where each dimension is a different unit?
Okay, enjoy sport problem maybe another example.
Enjoy sport problem would be another example. If you remember the enjoy sport problem with the 6 discrete attributes, 5 of them were binary and 1 of them was ternary. How do you measure distance in binary space? Well, you can call it 0 and 1, and the distance is 0 along that dimension if they're the same, and 1 if it's not. How do you measure it in ternary space? Well, you could define, I think it was sunny, cloudy, and rainy, or something like that. You could define 0, 1, 2 if you're assuming that they're ranked, but sometimes you have a categorical variable that is not ranked, is not naturally ranked. So how do you measure distances there. You could define that if they're the same, the distance is 0, and if they're different, the distance is 1. But a bigger issue is that even in the simple case of these 3 dimensions, so this is summed up to 3, you're combining the distance in sweat drops, meters per square, meters over second square, and decibels. But each one of these could be measured in different units. Instead of meters over second square, you can measure it in centimeters over second square. This would blow up this dimension by a factor of 100, right? It would change the numerical value here. It will dominate the distance measure.
Could you normalize?
Okay, what do you mean?
Well, if you know what is the maximum of the metric, just divide all the values by that, use the normalized metric.
Okay, so the idea is that you normalize each dimension by making the most positive and most negative observed values along this dimension go to a fixed scale from -10 to +10 or something. Just scale them back so that you could do that. And what do you think about it?
I was going to say, isn't the problem that we're assuming that each of these is equally important? Like maybe the distance between 2 points in terms of dimension 2 meters per second squared is more important than like the equivalent distance in sweat drops.
Mm-hmm. Right. I think that's the real problem. So yes, you could do that, but I agree with you that would assume, if we do that we believe a priori that all the dimensions are equally important in measuring the distance. And to remind you, we only care about the distance as far as it correlates to Daniel's assumption that nearby points tend to have the same labels. So, do we believe that nearby points defined that way have as much to do with sweat drops as they do with acceleration or with anything else? Not necessarily. In fact, if we did believe that, we would have a different problem, and that is that there may be a few dimensions here that are completely irrelevant. And if we insist on scaling everything, that they will get as much vote as everything else. And if you have 100 dimensions, and you don't really know in advance which of these are important, you will be completely dominated by the irrelevant dimensions. That will happen whether or not you scale. And if you don't scale, if you scale, you're just giving everybody the same amount of vote. If you don't scale, you give votes based on what units you choose. Did you use meters or centimeters? So compare that to decision trees. In decision trees, you can start with 100 different dimensions, 100 different attributes. But the decision tree building process will select the few attributes that it finds to be correlated with the answer, to have mutual information with the answer, with the label, right? So having lots of attributes doesn't hurt decision trees, at least not as much. You can have several thousand data points and several hundred attributes, and you will have a fine decision tree, even if those 100 attributes, 90 of them are completely random and irrelevant. Decision tree will pick up the right one. Nearest neighbor method, at least the way we're using it, will be completely overwhelmed by the irrelevant attributes. This all often goes by the name of curse of the dimensionality. It actually is used to refer to two different things. One is what I described just now, that you have lots of attributes, lots of dimensions, and you don't know which of these are relevant, and you're kind of overwhelmed, that your decision is overwhelmed by all the irrelevant ones. The second thing that this phrase is used for is when you try to estimate parameters. It's sort of related at a higher level. Estimate parameters, if you have a high dimensional model, the number of parameters you need to estimate is exponential. And then you quickly, as your dimension of the problem, if you scale up the dimension of the problem, you quickly run out of data and you are in a hopeless situation. It's kind of the same thing, because if you had enough data points, maybe you could figure out which dimensions are relevant, which are not. And in a way, this is what decision trees do. They evaluate all the dimensions on the criterion of mutual information with the label, direct mutual information with the label, and they make the decision based on that. And most of the time they'll be right. As you know, it's a greedy decision, so they won't always be right, but most of the time they'll be right. This nearest neighbors, at least the way we described it here, doesn't do any of that. It just takes all these dimensions as given and uses them as part of the definition of distance, and can get hopelessly lost if there are lots of irrelevant dimensions, or even if all the dimensions are relevant but they are scaled improperly against each other. Comment? Here's someone? Yes.
So isn't this the same problem with clustering always?
Yes, absolutely, you have the same problem with clustering. So let me try to give you a specific example where you have just two dimensions and nearest neighbor will be hopelessly lost. Actually, the real problem has only one dimension, and here's the data points for the real problem. This is the real problem. It's one-dimensional. And if we knew it was one-dimensional and we knew this is the only dimension that matters, nearest neighbor would work beautifully. Right? I mean, I'm assuming that the real divisions should be here. And, what could be easier than that? And nearest neighbor would solve it very well. But suppose that somebody now threw at you, when they gave you this problem, they thought there was another dimension that mattered, and they gave you both. So really the way you see this data is, like this. No, I have to make it more contrived than that. Let's see, what do I want to say? Would that work? Nope, that won't work either. I need to think about it for a moment. So the idea is, I'll forget about these for a minute. The idea is that you have two dimensions, but the y dimension is really not important. It's just there to confuse you. But it will confuse you if you put a data point, the pluses are here, let's say. Alright, this would do. If you now get a point here, in fact this whole area, the nearest neighbors in two dimensions are these guys. But that's because you took into account both horizontal and vertical distance. Now if you knew that the vertical distance is irrelevant, you would just squash everything down and you'll be in this situation and you will classify them as positive. This is sort of the simplest example I can come up with to show how irrelevant dimensions can confuse you. Okay, so we found that problem. There is something, I'm sorry, Shai.
Get the weight very low for one dimension?
A neural network will make the same problem. We'll have the same problem if you have two dimensions, because if you believe that they're both relevant, but a neural network you have, the difference is you have an error function, right? So the error function, following the gradient of the error function will push you in the right direction. And to the extent that the neural network is capable of representing the right answer, it will eventually find it. The problem with nearest neighbor is that you're not learning from the labels. Well, I shouldn't say that. Not in the same way. You're not learning in the same way. Well, I'm sorry. Let me take it back. Let me go back to the neural network. The neural network is given only this picture, right? So chances are, if you remember what neural networks do, they form smooth, continuous cells or regions to give their answers. So chances are, well, it would either pass the line here, or it would pass it like this, maybe. This is the most likely thing a neural network will do, depending, of course, on its topology. So it would do the wrong thing too. So it'll be fooled by the extra dimension as well. Now this is an extreme example where the data was arranged along the y-axis in a contrived way, especially to create the effect. You can imagine that if some attributes, some dimensions are not relevant, they're not going to be there deliberately to mislead you. They're just going to be random. Right? Random with, at least random with the sense of not correlated at all with the label. So the usual effect would not be as bad. But it could be still significant, especially if there are only 5 relevant attributes and 95 irrelevant ones. The cumulative effect would be devastating. So there is something we can do to think of how to scale those dimensions, and that is we can do something like leave one out, cross-validation, to try to adjust the scaling for all the dimensions. So the idea is that the definition of distance will be modified to be a weighted distance or a scaled distance. Here, you write it. Distance here, and I'll forget about the square, the square root. I can add it at the end. You have xqj minus xij squared times some weight j. This weighting, and I could take the square root again if I wanted. This weighing corresponds to, or is the same as scaling that dimension, the jth dimension, the j axis, stretching it or compressing it. If you believe this dimension is more important, you stretch it. That means a larger W. If you think it's less important, you compress it. In the limit, as W gets close to 0, if it is 0, it's like taking the dimension out. That means the dimension doesn't matter at all. Not having that attribute. Now you can think about learning these weights from the data. And the way you might learn them is by leave one out. Take all of your data, fix the set of weights, let's say fix them at all being 1. Take out one data item, pretend it's not there, and try to classify it using the nearest neighbor methodology. Do that over all your data points, see what the error rate is. Then change the weights. And do it again, and see if you get lower error rate. Now you're searching a very large space, the space of all weights, and there are n weights. But you can imagine searching along one dimension at a time. Fix all the weights and then finding the optimal weight of one dimension, and then fix that, and then take another one and finding the optimal weight along that dimension, and then fix that and take the third one, and so forth. So you could judiciously choose weights based on cross-validation, backtesting, leave one out, jackknifing, all refers to the same thing. Okay, so we dealt with the distance issue. What else can you tell me about the method overall? It's already been mentioned that it's sensitive to small fluctuations. If your nearest neighbor happened to have the wrong label assigned to it, then your decision is wrong, right? What can you do about that?
Take a majority vote between a few.
Take a majority vote between a few nearest neighbors. So instead of taking one nearest neighbor, take, let's say, 3 nearest neighbors and take a majority vote between them, or even 5. That does seem to reduce that risk. At what cost?
Computation.
Sorry?
Computation.
Computation. Yes, possibly. Now you have to find the 3 nearest neighbors as opposed to 1 nearest neighbor, although one could argue that depending on your algorithm you might get some of it for free. I mean, certainly the straightforward algorithm of just scanning all of them, calculating distances and keeping track of the closest one, it's very easy to also keep track of the 2 next closest. But depending, if you do it more cleverly, it might entail somewhat more work. That's right. Any other costs?
Introducing a bias.
Say it again?
Introducing a bias.
Introducing a bias. How come? How so?
Because you're smoothing the neighborhood of a certain point.
You're smoothing the neighborhood. Okay, so let's take a case of, let's say X is here, XQ is here. This is our query point. The 1 nearest neighbor will make its decision based on this guy, which is pretty good because it's a very close neighbor. But if we insist on the 3 nearest neighbor, find the 3 nearest neighbors, you have to go far out. You have to go to here and to here, which are quite far. So by forcing yourself to go out, if you're seeking more neighbors, you may have to go further. And as you go further and further, the relationship between your label and the label of the people you find becomes more tenuous. So it's the trade-off between how many neighbors you're going to average over in order to reduce the possibility of relying on an erroneous neighbor versus how far out you have to go, and therefore your neighbors become less relevant. You can think of extreme cases. I could put, a point here. Here's a plus point, and here's my query. And it has 1 very close neighbor, but lots of very far neighbors. And if you insist on having 3 or 4 or 5, it's going to get diluted by very far neighbors. So it was right for you to call it bias. In a way, it is bias.
The vote can be weighted by the distance itself.
The vote can be weighted by the distance. Okay? That's a good one. So what you're saying is, you want to consult more than 1 neighbor, but you don't want to give them all equal weight. The closer the neighbor, the more weight you want to give it. Okay? I like that. That seems to be sort of benefit all sides. So let's write it down in the formula. This is our distance measure. And we're going to create a vote. The label Q is going to be defined as, how do I write it? Majority. I think I'll write it as argmax over all possible labels of that's going to be complicated because now I have to have a sum of all the neighbors that agree with this label V. So let me just write it in words. Or maybe it's summarized in the slides in a nice... Yeah, in the slide it's already in the regression and we're still talking about classification. So let's just say weighted vote of, weighted votes of, and now we're going to have weighted votes based on, and now we're going to have the distance between XQ and XI, where I is some neighbors, and we're going to introduce some function of that distance. And I'm going to call it K. K is a function that is largest when the distance is 0 and becomes smaller as you move away. A very common choice for K is a Gaussian with the mean 0. But you could think of other functions, and it should capture exactly your belief about how the agreement of labels varies with the distance. How much stronger it becomes as you are close. I call it K because I use K because it is called a kernel function. Very important term in statistical methodology and nowadays in machine learning as well. Kernels are functions that, given two items, tell you how similar they are along whatever notion of similarity is relevant to the domain. So they are sort of generalized distance measures. They typically have the property that they have the highest value when the two items are the same item, the distance 0. There's an interesting relationship between kernels and traditional Euclidean distances. Okay, now is not a bad time to switch from thinking about classification to think about regression. So remember, the only difference is that the Y output is not a category, but a number, and you're trying to hit a number that's as close to the truth as possible. So now imagine that these are numbers, Y1, Y2, Y, these are all Y numbers, and we're trying to regress, given a new point in space, X sub Q, find a YQ for it. The nearest neighbor method would just say give it the same value of its nearest neighbor. Find which neighbor is nearest, and just like before we gave it the same label, we'll just give it the same Y. The K nearest neighbor, it's a small k, K nearest neighbor versus nearest neighbor. This is not the same K as the big K over there. The big K over there stands for kernel. This little k over here stands just for how many neighbors you're going to consult. 3, 5, 7. In the case of classification, especially binary classification, I stuck with odd numbered k, so that you can break, the vote would not be tied. That only makes sense for binary classification. For regression, you don't have to stick with an odd number. You could use 2 or 8 or 20 or any number k of your neighbors. And you can average them. And specifically, you want to average them weighted by their distance. So I'll write the formula for that, which is very similar to the formula I wrote here in words. We have a function that we're trying to learn from x to, I guess, y. So we have examples x1, y1, x2, y2. And we just store them away in the tradition of nearest neighbor. And then we're trying to estimate the value of the function on a new data point, xq. And it would be the average the weighted average of the value of the function on each one of the xi's. Now, because we use weighted averaging, we don't have to restrict ourselves to 3 or 5 or 7 data points. We can average actually over all the data points in our training set. In practice, the sum is going to be dominated by just the neighbors that are pretty close. The vast majority of our data points are going to have a contribution that's negligible, and you might argue that it's going to be a lot of computation and it's not going to help much. And you may be right. But conceptually, it is neat to be able to express the entire solution in terms of all the training examples, because you don't have to worry about which one is the closest. You just go over all of them. So you have a weighted sum of the values of the different inputs, I goes from 1 to n, and of course we have to normalize it by the sum of the weights themselves. So the w's have to sum to 1. One way we make them sum to 1 is by normalizing by their sum. And then the weights themselves, we said, are defined as a kernel function of the distance between the query point and the point we're interested in. And the kernel function could be thought of as a function of 2 points, or in this case the 2 points are first you calculate the Euclidean distance between them, and then the kernel function is a function on that Euclidean distance. You can think about it both ways. You can think about it, the kernel function is applying directly to 2 points, what's the effective distance between them, or you can say let's first calculate the Euclidean distance between them, maybe weighted, and then give it to a function that turns it into dependence, how similar, how much influence they should have on one another. Either way, in this case, the kernel function is a function of the distance, and you can think about it as being 1 over the distance, or 1 over the distance squared. This is what the slides do, that's what the book does, but you don't have to do that. The important thing is that you can now incorporate into the model your beliefs and your assumptions about the structure of the space. What's close to what? If you have reason to think that the dependence of the agreement of either the label or the y output varies differently with the distance, then you can plug it into your kernel function. Or, what happens more frequently, is you can try different kernel functions and see which one works best in the real world using held out data. So you see that a lot. You see a lot of people just plugging in, not squared, but raised to the power of 4 or some other fancier function. In fact, when we define distance, we said that the distance itself is defined as a weighted combination of distance along each one of the dimensions. You can think of that weighing as part of your kernel function. So in the most extreme case, you can think of the kernel function as doing everything for you. For any pair of inputs, or of possible inputs, it gives you out a value that tells you how related these two ought to be on average. And then you use that to make your weighted voting decision. So statisticians have been doing this for a long time, and this goes by the name of non-parametric statistics. Non-parametric statistics is called non-parametric because the alternative is when you assume a particular family of solutions like Gaussians or binomials or anything like that, and then the statistical estimation process consists of finding the value of the parameters. That's when maximum likelihood comes in, maximum posteriori comes in. Here we didn't make any assumptions except what does it mean for things to be close? How do you measure distance? Or, more accurately, given any two possible inputs, how closely related should their outputs be? Or are their outputs on average? That assumption is captured by the kernel. There's been a lot of work on choice of kernels. One of the most important rules of thumbs that came out of this work in statistics about choice of kernels is that the actual shape of the kernel function, if you think of the kernel applied to a distance, the actual shape of the kernel function is not as important as how fast it drops off. So often people use Gaussians, and since the mean has to be 0, the only choice you have now is the standard deviation. How broad is the Gaussian? That determines how far does the influence of every data point go. Now people have tried many other kernel functions. It turns out it doesn't make that much difference which family of kernel functions you use, but what's called the bandwidth of the kernel, namely the more or less the standard deviation, how wide it is the most crucial point. And since it's a single parameter, again, it's fairly easy to optimize on the data using leave one out. So I showed you how non-parametric statistics is used for classification, how it's used for regression. Let me show you how it's used for density estimation. In density estimation, assume that you have a one-dimensional function that gives you back numbers from a single dimension. And suppose you got back these numbers. They lie here. I don't know if you can all see that, these axes. Now you're asked to estimate the PDF, the probability density function from which these numbers came. One way you can do it is using parametric statistics, a parametric method. Assume a certain family and then estimate the parameters of the family, maybe using maximum likelihood. So a common family to assume would be Gaussian, and you just need to estimate the mean and variance of the Gaussian. And you can use the maximum likelihood criterion to choose those. So you can write an equation that says, here's the likelihood of these data points given any mean and standard deviation, and then take the derivative and find the mean and standard deviation that maximize that expression, and it would give you something like this. Right? More or less. Or you can assume a different family, let's say a mixture of two Gaussians, and say which two Gaussians were in positions on the data give the highest likelihood. Or you can assume some other continuous distribution, Poisson or anything else. The non-parametric alternative would be to not assume any global shape of the distribution, but to put a little kernel on each one of these data points. And the kernels would typically be Gaussians, but they don't have to be. So if you do that, then there's going to be a little Gaussian on top of this one, and a little one on top of this one, and one on top of this one. Of course, they can overlap. This one and this one, and this one. All the Gaussians should be the same height. I'm sorry, not the same height, the same area. I mean the same height. And now you add up. So there's no zero because Gaussians go on to infinity. So nothing is zero. And now you add these Gaussians together. And the shape that you will get would be something like some nondiscrete thing with bumps. Now, you looking at this example, you might prefer the parametric method. And you would be right to prefer it because you only have 5 data points. And when you have so little data, it's probably a good idea to make some assumptions, especially if you have reason to believe that the assumptions are right, that the data came from a Gaussian. But imagine you had 500,000 points. If you have 500,000 points, the bubble method, when you put a little bubble, a little Gaussian around each data point, and then you add them all up together, the bubble point will give you a very, very good, very accurate density estimation. Of course, it will get more and more accurate with more data. Whereas the Gaussian method will be stuck choosing only mean and standard deviation. It doesn't have much expressive power. So if the data did come from a Gaussian, you win, but if it doesn't, you're hopelessly lost. So the advantage of the non-parametric method is that it does not make many assumptions. The assumption it makes are very, very weak, and it allows the data to shape the form of the solution, and as you have more and more data, it can shape it more accurately. questions? Please.
Doesn't this kind of run into the same problems that we had with overfitting from neural networks and all the and some of the other stuff that we did, where we just assumed the most rigid structure for the data point, so fit every single data point exactly, and then assume a point and then work from there.
Does it run into the same problem? So the problem you're describing is with the polynomials.
Yeah.
And with the polynomials, we ran into this problem because we were trying to fit many data points. We were giving it as many degrees of freedom as we could to fit exactly. Intuitively, I don't see it running into the same problem because if you have 500,000 data points, each data point is given a tiny bubble, right? So it only contributes an area to the overall curve that is 1 over 500,000 of the overall area. So I don't see how one renegade point would distort significantly. But I do see some relationship there, and I'm not sure how to answer the rest of it. Generally, non-parametric statistics is superior where you have a lot of data, because it makes fewer assumptions. If you can afford to make fewer assumptions, of course it'd be better. Nearest neighbor, the method came from machine learning. The term came from machine learning as far as I know. But it can be thought of as a non-parametric classification. And nobody these days would use a standard nearest neighbor like a first nearest neighbor unless they are in an area that it's got so much data that it's guaranteed to be good. I mean, there are situations where you look at it, maybe the situation you were describing then, and it's obviously the right thing to do. But often people would use a weighted nearest neighbor. Take the 5 nearest neighbors, or take nearest neighbors that fall within a certain distance from you, not to exceed a certain distance, sort of balancing the distance with the number of neighbors. And of course, if you weigh each neighbor by their distance, you don't even have to worry about that. That balancing of distance with number is exactly the bias-variance trade-off. The reason you want to consult more than one neighbor is to reduce your variance. Your variance have to do not only with the possibility of error in the label of the neighbor, but also with the possibility that your assumption that nearby points, the underlying assumption in nearby points have the same label, this could be right most of the time, but sometimes would be wrong. So you want to consult more neighbors, average over a larger number, to reduce your variance. Another way to think about it is, as you move your point of query across the space, if you rely on the 1 nearest neighbor, its label would change much faster than if you rely on the 10 nearest neighbors. Because if you rely on the 10 nearest neighbor, when you move at a small distance, you may have crossed the boundary between who is your 10th nearest neighbor, but it may not change the majority. If you had 7 to 3, you might have 6 to 4 now. Your label will not change as often. So as you use k nearest neighbor, as k gets larger, the rate at which your label, your answer changes as you move the points, slows down. So that's another form of variance. There's not much variance. The answer varies less as you move the x, as you move the input. That's variance. So that pushes you towards a larger k. On the other hand, larger k means you're going further out. And further out means you're relying on neighbors that come from, in a way, a different distribution than you. They come from different circumstances than you. And therefore you have a bias. Another interesting relationship is what happens as the amount of data that you have goes to infinity. Imagine that you apply either 1 nearest neighbor or k nearest neighbor to an ever-increasing amount of data. So the density of the points in the space gets larger and larger and larger. So let's first take the 1 nearest neighbor. Remember, the method is very simple. You find your nearest neighbor and you provide that label. What happens as you have more and more data? As you have more and more data, you find your neighbor closer and closer to you. In the limit, your neighbor is right on you. It's an infinitesimally small point to you, so you can assume that it comes from the same distribution as you. So if it's a deterministic mapping from input to output, and if the mapping is continuous in the sense that infinitesimally small differences usually don't change the label, then as you have more and more data, you're going to be correct. The more interesting is the case where the function is not deterministic. Imagine that you have a label that's either plus or minus, but the probability that an input would get a label plus changes as you change your location in space. But for one particular location, it's still a probability. So if you sample the same location multiple times, you might get different answers. Now if you use one nearest neighbor with infinitely much data, you're effectively using Gibbs sampling. Do you remember Gibbs sampling? It's when you select one hypothesis weighted by its posterior and use its output as opposed to summing over all the hypotheses. So you can think, this is sort of an analogy for you just to think about, and it's described in the book. You can think of the entire space, the input space, as full of hypotheses. Each point in the input space, each location, is a particular hypothesis. And that hypothesis is probabilistic. It says with some probability you'll have a certain answer. And what you have here is this particular plus is one particular output came of this particular hypothesis that was here. So if you choose the nearest neighbor, you're basically choosing one hypothesis and looking at the output it generated. Similarly, if you think of k nearest neighbor, if the amount of data you have grows infinitely, and you allow k to grow with it, so k also goes to infinity, which is okay because you're staying in a small neighborhood. So not only are you staying in a small neighborhood, in fact, as the amount of data grows, you make the neighborhood smaller and smaller. So in the limit, the neighborhood in which you look is right on the dot, right where you want to be, but it still has infinitely many examples. Then you're in very good shape. You take the majority vote of labels that were generated exactly at that point, and what you get is Bayes classification, Bayes optimal classification. Because you will give the best possible label that you can. Your probability of error would be the lowest possible. In a way, if in that particular point there's a 70% chance of a plus and a 30% chance of a minus, then your best answer is to say plus, but 30% of the time you'll be wrong. And that's a Bayes error that cannot be reproduced. So there's a relationship between the asymptotic behavior of k nearest neighbor and Bayes optimal classification. Any other questions? So there's a lot of stuff we didn't get to, but that's okay. The whole purpose of this is to conceptually just to think about it. No, don't wrap up yet. See if we can squeeze something else in here. There's an interesting example in the book, in the slides, about case-based reasoning. So this is reasoning in a completely non-Cartesian space. It has to do with how to combine pipes in order to achieve a certain input-output flow of water, hot water, cold water, whatever. Do read it. The interesting point about it is that people use nearest neighbor reasoning in their everyday life all the time. If you think about how old people impart their wisdom on us, way back when old people had wisdom, I meant it as a way of making fun of us, not of old people. The way they do it is by consulting their memory and their experience and finding implicitly, without even thinking, the examples in their life that were most like the problem that they're facing right now. Right? So they may not do a Cartesian distance, but there is some implicit sense in which you find among many, many items which ones are the most relevant. And you tend to base your answer on that. And of course in the real world, that is just the first step. After that you need to make adjustments. In what way is this different and so forth. But a lot of what we do when we bring experience to bear is nearest neighbor matching. And it's matching at a very abstract space, not at a Cartesian space, but it's matching nonetheless. And often you will find this argument in court when lawyers bring precedents. And lawyers on both sides will bring precedents, right? this side claiming, here, these are precedents that say that just like this case, and you ruled it, and it was ruled that way, and the other says, no, I have 5 other precedents, no, they're much more like this case. And they start arguing is, which is the right precedent, which is the closest precedent. And what they're doing is they're arguing over a kernel function, or over a distance function, like, which is the right distance, which are the important dimensions that are more important and therefore dominate the answer. Okay, thank you.